All right, thank you. Yeah, so what I would like to talk about this morning is some of the work that we've been doing in California looking at maritime hazard. This first animation gives you some idea of the types of modeling results that we're using to come up with products that we give to the individual harbors so that they can assess the types of damage that they might have. So what you're looking at here on the larger image is the water surface elevation, and you have these tracers which might represent potential debris. And over here in the smaller plot, you see the velocity field underneath that water surface elevation. Right? So our motivation from the start was to try to better characterize the currents over here, thinking that there was a large set of possible tsunamis in harbors that didn't cause significant flooding, but still were vulnerable to damage because of the currents. And if you didn't get the currents right, you couldn't understand the possible hazard due to the tsunami. And so this just gives you some background. We'll talk more about the simulations as we go. So how do we try to get all this information to the individual stakeholders? How do we get it to the harbor masters, the captains of the port, the individual emergency managers that have to deal with the harbors when events happen? And so our focus has been to develop these types of playbooks. So the idea of the playbook would be you deliver a binder or some sort of set of information to the individual harbors where you have individual sheets or sets of sheets which correspond to a particular source. Okay, so you get information the day of the event saying that there's a tsunami from a location with an expected wave height. The person working at the harbor can look to their playbook, turn to the page which most represents that particular event, and get a very rapid estimation of the types of effects that they might see. The other advantage here, which I'll talk about later, is that with these playbooks, they're developed in coordination, in partnership with the individual harbor masters, the people making the decisions. So they look at the information beforehand and they think about the types of responses that they'll have for these particular events. So it's an iterative two-way process. So with these playbooks, we focus on the currents generated from a range of different tsunami sources. So we are scenario-based. We are not probabilistic. These are an example of some of these pages. I'll talk more about this a little bit later on, and I think Rick will go into this as well a little bit later on. So what is our current maritime modeling status in the state of California? Well, we've performed 10-meter resolution most simulations at about 35 harbor areas across the state. So this is many more marinas than 35 marinas, but 35 general areas across the state. For each of these, it's 5 to 6 source scenarios, and in that 5 to 6, we've included the 2010 and 2011 for all the harbors. What this allows us to do is it allows us to go back and hindcast the currents throughout the harbors and to match the predicted currents with the observed damages. The challenge, though, is connecting these model simulation results, these modeled currents, to the damage, right? So what the model output gives you, for example, here at the Port of LA and Long Beach is this for maximum current. So there's a lot of detail, there's a lot of resolution, there's a lot of information. This isn't necessarily the raw information that you want to give in a playbook that you want individual harbor masters to have to interpret either for planning or for response. So what you want to do is you want to be able to take this information and in some way convert it into potential damage. Okay, so to take this broad continuum of information and put it into discrete levels. So in order to do that, you have to connect current speed to damage levels. Okay, and this has been a focus of our work for a few years. We've added a bunch of new data points to this effort, and I'll go over this now. So we need to develop these current damage relationships. And so how do we do this? In California, for the past few events, we have a nice set of observations of damage at particular locations in our harbors. And even outside of California, we have a number of current observations. We haven't incorporated a lot of the 2011 harbor damage from Japan into this plot yet. There was a very nice paper that came out a few months ago in Waterways by a few Japanese researchers that will try to get incorporated into this as well, but we have not done that yet. And so what we do is we take the current speed from measurements and simulation and we plot it against a damage index, where this damage index is really a qualitative index. It's not a precise index, where the index goes from 0 to 5, where damage index 0 means no damage, damage index 5 means complete destruction, and you have a range of intermediate damage levels along the way. So damage index 1, the nav buoys start to move. Damage index number 2, that's when the most vulnerable infrastructure starts to get damaged, and then 3 and 4 indices are where things start to go bad, particularly bad. And what you see when you plot these up is that you do have a nice trend increasing upwards and to the right, which is what you hope for, a nice correlation between currents and damage. And furthermore, you can start to see thresholds if you stare at this scatter plot long enough, right? And so you see that there is some threshold where damage initiates around 2 or 3 knots, generally speaking. It steps up to moderate damage somewhere around 5 to 6 knots, and then you start to get into major to complete damage around 8 to 9 knots. Okay, so not precise, but it gives us these divisions which we can use to start to delineate minor areas of damage to major areas of damage. Another nice piece of information that you can do with this plot is you can get an idea of the individual, almost like a resilience of the individual ports and harbors. So if you look at this scatter plot, if you're along this yellow line, it means that for that particular event, the harbor experienced relatively low levels of damage with relatively high currents. So they were resilient to the currents. If you're on, that's the green line, right? So down here, low damage, high currents, yellow line, high damage, low currents. So where you want to be as a harbor is you want to be down here on this green line. That's where you want to be. You want to be able to be resilient to the currents. You don't want large levels of damage. What usually happens in engineering and maintenance is that you build something, you maybe maintain it for a few years, then you forget about it, it degrades, it becomes particularly vulnerable, and you wind up here on this yellow line. Then the tsunami event comes in, it destroys everything, you rebuild, and you find yourself back down here on this green line again. And then over the next few decades, the whole thing recycles again, and you wind up doing it over and over and over again. So one of our main motivations in this project is to get this type of information out to the individual harbors and try to find a way to motivate them to keep themselves on the green line. Right? Long term, it's cheaper to do that if you can find a way to give them the proper information, to motivate them to do inspections and repairs. Maybe this makes a large difference in the long term. All right, so what do these damage threshold maps look like? So this is a map for the port of the LA side, and this is from the 2011 Japan event. Okay, and so the 2011 currents at this particular location were not very strong, and what you see is that from the modeling, you only have these areas of blue, which is minor damage, more or less only near the gates and near the choke points. Okay, and so you don't typically have ships there, and that's what they found during this event. There wasn't really that much damage. So one of the advantages in California and a lot of places on the West Coast is that now we have personnel who have worked in these locations, and they have some experience with tsunami events. They may have been minor. Some places they were significant, but they have been relatively minor. So you can use this information as a baseline, as a threshold, right? So they understood what happened in 2011. So we take this same result and we apply it to a hypothetical large scenario, something from Alaska. And now it looks like this. Okay, so now you say, all right, so yeah, 2011, they say 2011, piece of cake, no problem. All right, but that was a low-level event. The potential that you have when you look at a map like this, you have potential for large to moderate damage in many areas throughout the port. Okay, so you start to find a way to introduce this information, get them to see it, get them to know it's there. All right, the other major piece of information that we include in these playbooks from the simulations is this time threshold map. Okay, so this gives you an idea of how long the event lasts, okay, and the maximum duration of possible damaging currents. So the way that these work, so if you look down here at this map, so this is the time threshold map, velocity threshold map for a current speed of 3 knots for the Japan 2011 event. And so these colors here are in hours. So when you see these orange reds, what it means is that 3-knot currents persisted at that location for 50 hours. Okay, so that it gives you, it puts the time dimension to it. For planning, for response, you know where these currents will be and how long they will last. Okay. Bring all this information on an example playbook page, and it starts to look like this. Okay, so you have the damage potential over here on the right, you have the time thresholds for different currents down here on the bottom, and then you have these sections of general information, specific instructions, and possibly things like safe areas for repositioning. The idea being that particularly down here for these two, they're completed with input from the harbor master. Okay, so the harbor master, the people making these decisions, have looked at these charts and they've thought about it. Okay, so it's not fresh when the event happens. The other piece of information from maritime that we've worked on in the past few years is this offshore safety zone, right? So the guidance as it was a few years ago said that all vessels should go out to about 600 feet, which is probably overkill. We have looked at current predictions throughout harbors in the state, and you can come up with a plot like this where you have water depth here in fathoms. If you can think in fathoms, that's great. If you can't, there are the conversions in meters and feet. And then maximum currents throughout the domain. And so what you see, generally speaking, throughout the simulations is that less than about 30 fathoms, something like 180 feet, you have high variability in currents. So that means that you're in the area where you can get eddies, you can get jets, places where the currents are chaotic, places that you really don't want to be. When you get above about 30 fathoms, you start to lose that variability. The currents are still somewhat strong, but you expect them to be straight line currents. So they're not a particular safety hazard. And then as you get into deeper and deeper water, that exponential decay of the currents continues. So we looked at this information, and the California Tsunami Steering Committee has accepted this 30 fathom safe depth, particularly for distant sources. So this is the number that the state will go forward with as recommending the offshore depth to retreat to, if you want to get out of the harbor. All right. And so what do we use these playbooks for, right? So we identify the areas prone to tsunami hazards, real-time mitigation to determine where planning for vessel movement should go, infrastructure controls, where to shut things off, where can we reduce damage. But it also has this long-term mitigation plan. So you put this information into the hands of the planners, into the engineers. You can start thinking about strategies to make the areas that are most vulnerable more resilient. Right, and so we're going to incorporate reasonable mitigation measures into these local hazard mitigation plans. So that's the idea, the feedback, the loop. All right, so some of the work that we've been doing now more recently, a few pilot study concepts. One I showed on that first slide, this idea of being able to model debris. Okay, so this is a large event in Ventura Harbor, and we show these to the folks down in Ventura Harbor, and it gives you this idea, right? So it's often easy to think of the rising and falling of the water level as almost a steady thing, but when you think about what can be transported by the currents, in the water, it's much more like a blender, right? So it doesn't matter where the debris came from, it all gets mixed together, it all gets churned, it turns into a giant mess. And so that's what you'll start to see here as this goes on, right? So right now what you're seeing here, these are just they're just massless Lagrangian particles, so they're just fluid tracers. Eventually we can do better than that. We can include some properties of the debris and some feedback into the water itself. Right, and so these provide visualizations of the possible spread of debris or the likely places where debris might settle. So again, a piece of information that you can be aware of as you move forward with the mitigation plans. And if they're just Lagrangian particles, this is just post-processing. So, this is a useful tool for visualization, but it can be done with any simulation if the currents are right. It's just a post-processing step. If you know the velocities, you can do it. Okay, another piece of information is sedimentation and scour. So this is a tricky one. What you see here is the measured seafloor depth change before and after the 2011 event here in Santa Cruz and here in Crescent City, and these are modeled results. So order of magnitude, they're similar. There's actually a talk from one of my former students tomorrow. It's really good for these locations to know which areas will be scoured, where the sediment will be deposited. You can even incorporate that into long-term sediment management plans if you're clever enough. The challenge with sediment transport modeling across the spectrum of sediment transport modeling is that someone can always say that it's wrong, right? Sediment transport modeling is really, really hard, particularly when you're dealing with complex currents and the complexity that we have here with tsunamis. The last thing I'll talk about here is this scenario-based failure probability. So you can actually start looking at individual infrastructure assets and trying to start understanding how they might fail. So for example, if you look here at Santa Cruz and you look at a few different locations where the slip and boat orientation is different, you can then come up with capacity and demand curves to come up with estimations of when they might fail. Okay, so you can't really see these too well here, but this is tsunami current and tsunami direction or current direction, and these are contours of probability of failure. So when you get to the right of these curves, you're very likely to fail. If you're to the left of these curves, you're in a good area. And you can start to plot up where the maximum currents will be for a whole different range of sources. So you can look at this and say, well, all right, for that particular event, these docks are going to fail. But in this location, the docks are probably going to be fine. Okay. So in conclusion, we have these tsunami current-based hazard maps with a range of things. We're looking next to develop scenario-based sedimentation and scour and infrastructure vulnerability methods. The last thing I'll leave on this, currents, big challenge. There's lots of maritime work trying to go on now. In February, the NTHMP is funding this modeling and mapping benchmarking workshop specifically to look at currents. The website is there up on the top. If you're interested in this, come talk to me, come talk to Rick Wilson. We'll give you more information about it. Thank you.